Chapter 8, Chemical Equations. Here we see a picture of aluminum foil reacting into liquid bromine. And there are YouTube videos on this where it's a pretty violent reaction. But what's important in this chapter is we're going to learn how to express this reaction in a chemical equation. So chemical equations are shorthand notation that chemists use to write down what happens in a chemical reaction. And it's useful because it's universal. All chemists write chemical reactions in the exact same way, regardless of what language they speak or what alphabet they use, because everyone uses the exact same symbols on the periodic table. Reactants are what you start with. Those are on the left-hand side of the arrow. So what we start with are reactants, and they're on the left. What you produce, you don't start with it, but you make it in the reaction. Those are products, and they're on the right-hand side of the arrow. And then we can read the arrow as yields. So the reactants react to yield the products. So the general structure of chemical equations, reactants are on the left, we have our arrow, and then products are on the right. And the small letters stand for coefficients. Those would be a number saying how many moles reacted. And the capital letters would be the actual chemical symbols for what's reacting or being produced. The coefficient 1 is not written in a balanced equation, it's just understood. Because if you had none of that chemical, you wouldn't even write the symbol. And so if there's no coefficient, that's an implied 1. The delta sign above the chemical arrow again means heat. Typically the capital Greek letter delta means the change in something, but this is an exception. In this case, when you see the delta above a chemical reaction arrow, it means a lot of heat was applied. And in parentheses, we can put G if the state of matter is a gas, L if the state of matter is a liquid, S if it's a solid, and AQ for aqueous, which is from Latin, aqua, which means something is dissolved in water. And again, we can read the arrow as produces or yields. Reactants are on the left side of the arrow. What you produce is on the right side of the arrow. And then we put the state of matter in parentheses, solid, liquid, gas, or aqueous, which means it's dissolved in water. And then the delta sign is for heat. Law of conservation of mass. The total mass of the reactants will be equal to the total mass of the products. You do not lose mass, you do not gain mass. The mass you start with is the mass you end with. No creating mass, no destroying mass. If you start with 100 grams of water and we decompose it using electricity, you will get 100 grams of hydrogen and oxygen gas, but you do not lose or gain any mass in a chemical reaction. Balanced chemical equations. In chemistry, you don't create atoms or destroy atoms. You're just rearranging how they're bound to each other. And so all the atoms that you have at the beginning, you have to have at the end. And so the balancing equations is like chemistry accountant, where you make sure you have the same number of each atom, of each element on both sides of the arrow. So mercury oxide, this can be easily broken down to mercury and oxygen by heating it. And again, you'll notice that the metals that were known in the ancient times are really easy to purify. And that's why they had them in ancient times when the science of metallurgy wasn't very sophisticated. And so that's what metallurgy is. People, they take minerals and they figure out how to get the pure metal out of that rock. And so here we heat mercury 2 oxide to get mercury and oxygen. But is it balanced? Do I have the same number of each type of element on the left and the right? I have one mercury atom on the left, one on the right. But I only have one oxygen on the left, and I have 2 on the right, so it's not balanced. You can only change coefficients. You're not allowed to change subscripts because that would change the chemical itself. So here, we put a 2 here. Because now I have 2 HGOs, which means I have 2 mercuries and 2 oxygens. Now my oxygens are balanced. I have 2 on each side of the arrow, but my mercury is not balanced. I have 2 mercuries on the left and only 1 mercury on the right. And so I'll put a 2 there, and now I finally have a balanced equation. I have 2 atoms of mercury on the left of the arrow. I have 2 atoms of mercury on the right of the arrow. 2 oxygen atoms on the left of the arrow, 2 oxygen atoms on the right of the arrow. And that's what makes this a balanced equation. I have exactly the same number of each element on both sides of the arrow. Because again, you do not create atoms, you do not destroy atoms, we're just rearranging how they're bound. So a balanced equation has the same number of each type of atoms of each element on both sides of the arrow. And you want it to be the lowest possible ratio. So 4, 4, and 2, it's not wrong, but it's not the most correct form. 2, 2, and 1 is better. So if you get a case like this where all the coefficients are divisible by 2, then divide it by 2. But you want the smallest whole numbers that are possible. So here, magnesium plus oxygen burns to produce magnesium oxide. And we have our skeleton equation. 1 magnesium on the left, 1 magnesium on the right. 2 oxygens on the left, 1 oxygen on the right, not balanced. So we'll put a 2 in front of the MgO. Now I have 2 oxygens on each side of the arrow, but now magnesium's not balanced. I only have 1 on the left and I have 2 on the right. So I put a 2 in front of magnesium. Now I have a balanced equation. I have 2 atoms of magnesium on both sides of the arrow. I have 2 atoms of oxygen on both sides of the arrow. It's a balanced equation. And this is really important for the next chapter when we get into stoichiometry, because to have the correct stoichiometric ratio, you have to have a balanced equation. So this is feeding up to next chapter. So potassium chlorate, when heated, breaks down to form potassium chloride and oxygen. Well, each side has 1 potassium, that's good. Each side has 1 chlorine, that's good. But the left has 3 oxygens and the right has 2. And the smallest number 3 and 2 go into is 6. So we put a 2 here to get 6 oxygens on the left. We put a 3 here to get 6 oxygens on the right. But now potassium and chlorine aren't balanced. There's 2 on the left and only 1 on the right. So we have to put a 2 there. And now we finally have a balanced equation. 2 potassiums on the left, 2 potassiums on the right. 2 chlorines on the left, 2 chlorines on the right. 6 oxygens on the left, 6 oxygens on the right. Balanced equation. So let's do another one. Silver nitrate reacts with hydrogen sulfide to produce silver sulfide and nitric acid. We first put down our skeleton equation. And now we see there's 1 silver on the left, but 2 silvers on the right. So we'll put a 2 there. If you're using polyatomic ions, do not break them up if possible. So like nitrate, keep it together. A nitrate is an NO3. If you try doing nitrogen and oxygen separately, it's just going to make your job a lot more difficult. So make life easy on yourself and keep polyatomic ions together. Sometimes it's not possible because you'll get reactions where OH minuses and H pluses are combining into waters, but most of the time you can keep a polyatomic ion intact, and that's the easiest way to do it. So now I have 2 silvers on the left, 2 silvers on the right. And I have 2 nitrates on the left. Notice I'm just dealing with them as a polyatomic ion. I have 2 nitrates on the left, so I'm going to have to put a 2 over here to get 2 nitrates on the right. Now I have 2 hydrogens on the left, 2 hydrogens on the right. 1 sulfur on the left, 1 sulfur on the right. I have a balanced equation. Write the balanced equation for the combustion of butane gas, where carbon dioxide and water are the only products. Natural gases are the only fuel that burns perfectly and produces only carbon dioxide and water. But that's why you can burn a gas stove in your kitchen and it's fine. That's why we can run Bunsen burners in the lab and it's fine. Because natural gases are the cleanest burning fuels that there are. They burn perfectly and they only produce carbon dioxide and water as wastes, which is the absolute most perfect combustion you can get. So here, B is our skeleton equation. C4H10 reacts with oxygen to form carbon dioxide and water. That's the skeleton equation. To balance it, I have 4 carbons on the left. I need 4 carbons on the right. And now I notice I have 10 hydrogens on the left, so I put a 5 over here. I have 10 hydrogens on the right. And that gives me, before they put the 6.5 there, if I go back to the skeleton, I have 2 oxygens on the left, and now with the 4 and the 5, I have 13. So what times 2 gives me 13? 6.5. But you're not done yet. You're not allowed to have half of a molecule. There is no such thing as 0.5 of an oxygen molecule. So in a case like this, we multiply every coefficient by 2 to make sure that we just end up with small whole numbers. Which is why you got the double numbers, giving us the answer of C. Again, you had to double all the coefficients because you're not allowed to end up with just half a molecule. You either have a molecule or you don't have a molecule. There are no fractions.